So let me introduce, again, Neil Thompson, who's going to speak about the computational limits of deep learning. Take it away, Neil.
All right, thank you, Eric. Everyone can hear me?
Yes.
Great, okay. So the paper I want to talk to you about today is called the Computational and Economic Limits of Deep Learning. But it might, in other terms, be called sort of like, where is machine learning going? And some of this comes out, I remember a discussion that Eric and I had a number of years ago where sort of deep learning was starting to take off, and at that point it hadn't sort of crested, and I looked at some initial data and it sort of looked like a number of other things. And I remember Eric saying, well, this is really taking off in a very different way, and obviously the last few years have sort of really spoken to that. And so what I really want to talk about today is sort of the rise of that and where it might actually go. Okay, so that's sort of the background for this. Now, for those who aren't as familiar with this, I want to start by just saying, when we talk about AI and machine learning, we're clearly not talking about machines that think. Okay, I think often we're talking about rebranding of existing data science techniques, right? Like there are a lot of people who do regression who now call themselves machine learning experts, right, and get a higher pay because of it. I think that's, I think there's a lot of good work being done there, but I think that's not actually where the discontinuity has happened with what came about, say, 5 to 10 years ago. I think the big difference is deep learning, or what used to be called neural networks. Now, this is actually a little ironic because neural networks are actually, many, many decades old, and I'll talk about that. But this is really where there has been a noticeable change, and almost all of the sort of big benchmarks that have really been broken have come about through deep learning systems. Now, just to give you a sense of like how much more important this is, so earlier this year I did a survey of some of the most advanced computing users in the United States. So these are the national labs, some universities, some of the biggest companies that do compute. And I asked them, what's the most important machine learning technique that you use? And it's not even close, right? Neural networks, 3 to 4 times as big as the next closest one, which is regression, and then other techniques follow way behind. Okay, so that at least starts us on the path of saying, okay, it seems like neural networks are this big difference. And so what I want to talk about today is neural networks, or their modern form of deep learning. Why has that actually been so transformative? What's going on? Why has this been so successful? And then pushing forward to the future, is continued progress in deep learning economically sustainable? Okay, so to preview where I'm going to go, I'm going to tell you that neural networks are and have always been constrained by computational limits. And this is just very fundamental to the statistics of how they work. And I'm going to show you that improved deep learning performance requires exponential increases in computing power to get better. And that's clearly going to be a challenge, right? I mean, any sort of thing that we're going to try and draw on exponentially is problematic. Sources of future computing use are going to be expensive. As Moore's law winds down, we're going to have to use things like just using more chips to do these things, and that's expensive. And that means that in some areas, deep learning is going to become uneconomical, continuing to prove it. And what I think that's going to do is then it's going to push us towards more efficient algorithms and more towards what we have traditionally thought of as data science as a way to get this. Okay, so let's start with why neural networks didn't succeed in the 1950s. So people may know 1958 is when Frank Rosenblatt at Cornell first introduced the idea of neural networks. And he was drawing upon this inspiration of the brain as an analogy. And he said, look, I can have this idea where I have some sort of input, what we would now call a feature, but he was saying, the sensory system like the retina, and it's going to lead to this sort of series of operations which will then either fire or not fire a neuron in analogy to our brain. Now, we today would say, okay, well, this is, we now call this input layer, which is the sensory part, and then we typically have sort of one hidden layer, which we might call like latent variables. We often think about that, and then some output that determines cat or dog or whatever. Now, what's really interesting is literally in this inaugural paper, he recognizes the potential of neural networks. So he says, the simulation experiments have gone a long way towards demonstrating the feasibility of a perceptron as a pattern recognizing device, right? So this idea of pattern recognition as being the thing that's really important, and we think is what neural networks do even today. But also that there are computational limits. He says, as the number of connections in the network increases, so these connections here between different parts, as that increases, however, the burden on a conventional digital computer soon becomes excessive. And this is something that he recognized there, nevertheless, there's sort of a uptick in the number of neural network research that's done. And a lot of that comes to a head and then to an end ultimately with the work that Marvin Minsky and Stephen Papert do, where they publish a book and they say, actually, effectively, these three-layer networks, which is all that you can do with the amount of computation that people had, this is just basically a form of logistic regression. And that because of that, people get stuck in what is called the XOR problem. And you can think of it this. So if you think about logistic regression, trying to classify things into different categories with a linear separator, you have this problem here where any linear separator through here is going to put some of the ones on one side and some of the zeros, ones on the other side, and we're vice versa for the one. So you can't do perfectly with this as a method. And so in 1969, they proposed a solution to this. They say, the experiments, however, discovered an interesting way to get around this difficulty by introducing longer chains of intermediate units, right? That is deeper networks. Okay, so that's what we do, and we are implicitly, when we do regressions and we start adding interaction terms, we are basically doing the same kind of thing with them, which is of course how we would solve in economics this idea of an XOR type of problem. Okay, so why, from a theory point of view, why does deep learning require so much computational power? And here it's useful to start with some work that Andrew Ng did. So people may be familiar, Andrew Ng is at Stanford and has done a lot of pioneering work in this area. And he said, look, I think the relationship between these different types of neural networks is the following. So if you think about the data size here on the x-axis and model performance on the y-axis, this red line here represents traditional machine learning algorithms, which, for our sake, let's think of things like regression. And he's saying initially, when you only have a small amount of data, they do quite well, but that as the amount of data that goes up improves, that you get much better model performance. Okay, so this is, I think this is, we seem to think that in the big data world, this seems to be true. But I want to propose that this is actually not really a neural network thing. This is actually a much broader category that we should think about in terms of how we learn from data. And when I think about this from the point of view, we call it like an experts versus flexible learning. So from the point of view of economics, let's think about some data generating process, right? And we'll put it a simple little linear model. Now, we often do something which we'll call like the expert approach. So we sort of know an area and we say, I'm going to use my judgment to pick some number of these x's that I think are important. I'm going to throw them in a model where I also know some of the y's, and I'm going to estimate my parameters, right? That's pretty reasonable. The challenge is, of course, maybe we might miss some of the important x's that we should have in our regressions. The sort of more traditional machine learning statistical approach is to be very flexible. It says, look, I'm going to throw like many of those x's, maybe all of those x's that I can gather into my regression. That's good, but the problem is it's going to require a lot of data to actually estimate. Okay, so here we get a trade-off here, and it's basically a trade-off in how quickly you learn. And so there's sort of a fundamental theorem in statistical learning about how fast you can learn, the fastest you can learn. And you can see here that we have the sort of traditional square root of n on the bottom there. That's what we sort of think typically of how we make our sample bigger in order to get more statistical power. But at the top here, we have this d, right, which is the number of dimensions that we're trying to solve this in, or another way of saying is that the number of x's that we're solving here. And that this is really the curse of dimensionality. As we have more and more dimensions, it takes us longer and longer to learn. It takes us more and more data to learn from. And to put some scale at this, so I think it's useful to think about sort of the model that is used that's the current best performance in image recognition. So that model has 480 million parameters in it, right? So that's like the number of things within the network that you're trying to estimate. And if you think about that, that means that this type of model is going to require about 5 million times as much data as if you were trying to do some expert model that only had 100 variables. Okay, so I just want to get some sense of the amount of data here is huge. Okay, now there is one potential thing that can save us a little bit from some of this, and that's regularization. So in economics, we know this more usually through lasso, but it's this idea of don't estimate everything. Say, assume that most of those things are going to be zero, and try and find the few that are actually really meaningful to your regression. So you still throw everything in, but it's going to try and use some selection mechanism to pull out the most important ones. And what happens when you do that is that now you can sort of limit yourself to the most important ones, the real ones there, but you still get sort of this log D on the other side, which is just saying you still have to search through a lot of things, but it's just not as expensive as going through all of the dimensions in their full weight. Okay, so let me actually give you sort of a simulation that will tell you how this actually plays out. So let's imagine that we have a setting where there are 1,000 possible x's that we might throw in our regression, and there are 10 true ones. Okay, and we're going to have 4 different models that we'll compare. So the first will be the oracle, and this is sort of a term used often in computer science to say this. It just knows. It knows the answer. So it's going to have exactly 10 parameters in the model, 10 x's, and it's going to get all 10 of them exactly right. Then we're going to have an expert, and we're going to make this expert quite good, right? This expert is going to also include 10 things in the model, and they're going to get 9 correct. And then we're going to go the complete opposite side. We're going to say completely flexible. We're going to throw all 1,000 x's into the regression, and there are going to be 10 that are correct. And then we're going to do regularized, where you say we're still going to throw all 1,000 in, and we're going to find the 10 that are correct because they will be included in there, but we're going to use this sort of more efficient way of trying to narrow it down. Okay, so here's what you get when you actually do. Oh, and I should say, by the way, from our point of view, we should think of what we do in economics is almost always this sort of expert model, and what's done in deep learning is almost always this regularized model. Okay, so here's what you see in terms of how things learn. So here on the x-axis, we have the number of data points that you have, and on the y-axis, we have a measure of performance. And if we start with the blue line here, this is the oracle, right? Nothing can do better than that. It knows exactly what to do. It does it very well. Now, not surprisingly, the expert who knows 9 of the 10 correct ones actually also does quite well initially, but then it peaks, right? And that's very natural because it's missing one of those important x's. It can never do better than getting 9 out of the 10 correct, and so it plateaus pretty quickly. In contrast, the really flexible model here that just throws everything in takes a long, long time, right? You need close to 1,000 observations before it starts getting good, but then it does do good and does considerably better. And then here you have the regularized version, which as you can see, also learns very quickly, but slower than the expert, but much more quickly than the flexible one. Okay, so what this is telling us is sort of when you have these very flexible models, they can do quite well. Right? And deep learning happens to be an example of a flexible model, but it's not at all the only one. And I think it's actually a mistake to think that it is neural networks or deep learning that has been particularly remarkable at this. I mean, I think it has been implemented very efficiently, which is super useful. But there are proofs that certain types of neural networks, for example, can be replaced by a Gaussian process and do just as well. So it belongs in this class of what we call universal function approximators, which all do well eventually. And the question is just how well they do in small samples.
So, Neil, there's a quick question from Dylan Walker. Sorry, can you describe a little bit of the data that's generating these plots and how robust are they?
Yeah, so this is using that data generating process that I showed you before. So we're just assuming we have a series of these independent x's that contribute towards the y. And
so they're all equal. All the x's are equally important, and they're all orthogonal.
Correct. Exactly. So these are just random draws in, and then the system is learning.
There's exactly 10 that are important, and the others are 100 completely unimportant.
Exactly. Correct.
So you could imagine that the other ones have some small importance, and then maybe the regularized one would not. Yeah, eventually, the flexible one might catch up. Or is that right? Is my intuition right?
So so that's absolutely right. Yep. But you can imagine, like if you'd say, well, if I think the right number is instead, like, there are 10 really strong ones and then another really 40 weak ones, you could also still just do the regularized version with 50, right? That would still be much more efficient than trying to estimate everything.
Right. I guess the more general version is, I mean, this is a really interesting plot. It might be interesting to do, or maybe you do in your paper or whatever, a few other ones that have, slightly different sets of assumptions and see how they compare.
Yeah, I think, yeah. So that we have not done that yet, and we can think. I need to think about how how much difference we would get, but I think it's a really interesting question.
Well, and if there is no difference, that's interesting too. But yeah.
It might be nice to just be able to say that.
Yeah.
Okay, but one of the messages from this is clearly, right, that these flexible models of any stripe, if you have a lot of data, should be able to do quite well and considerably better than experts. And so I think this is really what you see if you think of something like.
Just one more question on that plot. Shouldn't it be a version of this that looks more similar to Andrew Ng's chart?
Well, so in some sense, this is actually sort of basic. This is basically Andrew Ng's model. Oh, well, okay. You mean like the size of the neural network?
Yeah, I guess it's pretty similar. It might be neat to more tightly map them together to each other. But well, yeah, I think that's the point you're trying to make, right?
Exactly. Well, yeah. I mean, in some sense, so the ones that correspond to his model are this green one and this red one, right? So the green one is the sort of traditional machine learning in the way that he would call it.
Yeah.
Right?
Okay. Good.
One is the lasso, and you can see that it performs less well and then eventually supersedes.
Yep. Okay. Excellent. That helps.
Great. Thank you for the clarification. Okay, so you can see that once you get big enough data, deep learning should be doing much better. And in fact, I think that's what's happening with things like the Google data center cooling example, right? So here, they have big data center, they're trying to cool it. They have many engineers working on this because it costs them a lot of money to do this. So they're trying to do it better. Nevertheless, when they let deep learning do it, deep learning does 40% better. Okay, it drops their cooling bill by 40%. Why? Well, because there's a huge amount of data that it can do, and the underlying process there, I mean, if you think about the sort of turbulent flow of air moving through one of these data centers, actually that's sort of very complicated, and so a flexible model is likely to do a lot better. Okay, all right, so this is the good news about regularization, right? This idea of narrowing it down that you can learn more quickly. The bad news is it helps you almost not at all with computation. And I don't have enough time to go through sort of all of why that's true, but it's basically because you are searching through all of these different possibilities. And so here's actually that those same set of models that we were looking at before. And now we've just said, okay, well, here's the performance you're going to get. And here's the amount of computation you had to do to get there. And what you can see is, of course, again, the oracle at the bottom here does very well. It learns very quickly. But you can see both the flexible and the regularized version take a huge amount of data to start doing well, and take about, a huge amount of computation to do well, and ultimately end up using about the same amount of computation as time goes on. And that number is like 1,500 times as much as these oracle models, right? And so this is a huge difference if you think about the amount of computation that actually has to be done. Okay, so let's now turn to the rise of deep learning. So I won't go too much, but of course, I think a lot of it comes to our attention through things like the important victory in Go. But it's important to understand that alongside this increase was a huge, this increase in improvement was a huge increase in computational power being used. So this is some data from OpenAI, and they're just saying, let's pick all of systems that are using deep learning of any type. So some of these are going to be like game playing, some of them are going to be image recognition. And what they show is that over this 6-year period, the amount of computation goes up by 300,000x. Okay, which is, I mean, to put this in context, that is way more than all of the benefit that Moore's law has given us since the beginning of computing. Right, this is a huge increase. It's also useful to put this on a longer scale. So this is some work that I've done with one of my students, where we said, okay, let's take the OpenAI graph, which is this one, and then let's plot this with Moore's law. And what you can really see here is that for decades, the stuff that was being done in neural networks was scaling exactly with the increase in computing power coming from just regular improvement in semiconductors. And then it's only really with this model in 2009 that you start to get this takeoff and the increase in deep learning and the amount of computing power that it's using.
So Neil, you've done a lot of work on Moore's law, but so there's 2 ways you could get that deep learning curve to go up. One is that they have different chips, so maybe Moore's law is not the fair thing if you use GPUs and TPUs and other things that maybe are giving you that. Secondly, there's the brute force method of spending a lot more money. How much would you allocate to each of those, or is there something else I'm missing?
Yeah, so the benefit that comes from moving to the specialized chips is something like 30 to 35x. So it's a fairly small chunk of the 300,000x that actually comes along here. So a lot of that jump that you're seeing is actually coming through brute force. It's from using many more chips for much longer time periods. Okay, so let's now turn to OpenAI has discovered this. What we wanted to say is, like, in that previous chart, we're really comparing apples to oranges here. What we really want to do is say, within particular domains, how much is it relying on computing power? And so what we do is we actually go, and I'm just going to click through this for time reasons. So we go to more than 1,000 papers in archive, and we pull out how well they're doing on a bunch of different benchmarks in deep learning, and then we actually estimate the amount of computation that they're using. And I'm going to show you one of those today, which is image classification. So people are, I think this is probably the most famous one. It was the one that started it, this performance on ImageNet. So here, what you can see with this is, you can see here we've normalized the amount of computation on the x-axis, and here on the y-axis we have the percentage error. So of all of the guesses it's making about what type of image it's looking at, how often is it making an error? And what I want you to notice is, like, how well this regression line is actually predicting this, right? So RR squared is 50%. That's just, we're predicting a huge amount of the variance in these models, in the performance of these models. And you can see also that this is a very shallow line. And why does that matter? Well, it matters because if you think about something like using image recognition in the car to recognize what's going on outside, right? You don't want to have these sort of 10, 11% error rates, right? You want something like a 1% error rate. But a 1% error rate with this is going to mean that you need to take the sort of current state of the art, and you need to increase the amount of computation being used in it by 1.3 million times, right?
There was just very recently, there was a paper out by the guys at OpenAI saying that to get the same performance on ImageNet, they could do it with 44% less compute over time. So there's been big improvements in the algorithms. You want to just comment on that? Is that enough to move that line much, or is that paper accurate?
I actually have a slide on that. I saw that come out too. I think it's super interesting, but what they're talking about is something like a 40x change, yep. Right? We're still nowhere close to being able to get to the kind of performance we want to with that change. Okay, this is a particular regression line. You could also say, well, I would rather have the lower envelope. I'll just say you get to basically the exact same thing. So we looked at this, and we looked at this in image recognition, object detection, question answering, name identity recognition, machine translation. You always see this pattern, right? And it's not surprising, because it is just about the fact that if you have a neural network, what you do, right, is you build these incredibly flexible models, and those models mean you need to have way more parameters than you have data. But of course, as you have more parameters, that also means that you need more data to train, and so both of these things grow very quickly. And so you get to this very rapid growth in the amount of computation that needs to be done. Okay, so my last couple of minutes here, let me just talk about why this ultimately comes back to something I think we care about as economists. And so this is drawing on some work that was done in 2019. And what they're showing is, like, actually, if you just think about some of these models that have been done in deep learning, okay, how much energy consumption has actually been taken by doing that, and what's the actual cost of just running those models? So, and what we're talking about when I say running these models, I mean training the model. So you have sort of the network, and then you train it with data, training it once, right? And so, of course, that means if you're like going to train it a bunch of times because you realize you made some mistakes, or you want to refine it, like, you're going to pay this multiple times. And what you can see is that, the costs range from sort of like $100 every time you run it to more like $1,000 every time you run it, to some of these really big models that Google is trying to implement, where they're trying to find like the most efficient network to do something. And then you're talking about literally millions of dollars to run. Now, of course, the point I want to make here is, if you're already in thousands or tens of thousands of dollars, right, exponential growth in the amount that you would do is totally infeasible from an economic point of view. Most people wouldn't pay it. And it's actually, we already have evidence that this is really expensive. And so let me jump to here. So, Google DeepMind, which has been undoubtedly one of the most successful implementers of deep learning, lost $500 million in 2018, right? AlphaGo, it's estimated that the cost of training it was 35 million. Okay, so I think the challenge we have here and where we're getting to in the paper that we'll hopefully be submitting quite shortly is, you can actually project these things forward and you can see that it's very quickly going to become the case that you don't want to use deep learning as the way that you get to some of these outcomes. You want to move to a more efficient machine learning algorithm. For those who are interested, I'm happy to talk more. I want to leave some time for questions, but some approaches that people have talked about for how you might be able to do this. You might use these more efficient things. So Eric already hinted at this. Most of these really do not have much of a big effect. I mean, you might get a factor of like 2x, not that big a deal.
Oh yeah, there you go. Okay, never mind.
Think about things like meta learning and transfer learning. This actually takes us in the wrong direction. It doesn't seem like it would, but the problem here is that in order to take what you learn in one area and move it to another, your performance gets worse, right? And so if you think about that curve I draw, the meta learning curve would be a translation of that. And you can see that, like, in the stuff that people have done on this, they found that if you, in ImageNet, for example, if you just take the same objects and you move them to different poses, the accuracy of the models goes down by 45%. And even if you take the same objects in the same poses and just use new data, you don't just let them retrain on the same data all the time, you get an 11% drop in accuracy. So both of these indicate there's just a huge drop that happens when you do this meta learning. And so this problem gets worse, not better. And then you can say, well, what about sort of customized computer hardware? So there's like quantum and things like that. I think the only one that really has enough potential there for the longer term is quantum. And that's only like if it works. And I had a really interesting discussion with a quantum theorist the other day, and she has not yet been convinced in any way that any of the algorithms that we have to do machine learning on quantum will actually allow us to do anything more efficiently than we can do on a modern computer. So that's kind of a challenge to that. Okay, so what did I tell you? I said that neural networks are and have always been constrained by computational limits. This is fundamental to the statistics, how they work. They're just very flexible models, and that limits them to how efficient they can be. Improved deep learning performance requires exponential increases in computing power, and that means that exponential part is not too bad when you're in the time of Moore's law, and it's a real problem when it's not, because it means you have to buy more chips, and that's very expensive. And what that means is that deep learning is going to become uneconomical in many places, and that's going to push us towards more efficient algorithms and away from this technology, which has really revolutionized machine learning over the last 6 or 7 years. I'll stop there.
Terrific. Thanks, Neil. I think we have a minute or so for if there's any questions anybody wants to ask.
Yeah, so I'll address, I see Dylan Walker has a question. So models can be updated instead of trained from scratch. So that's absolutely true. The challenge is going to be, like, if you want to get, like, the whole thing about over-parameterization is that you often, as you get more data, you often want to use an even bigger network. And so, like, many of the gains that you would want to get, you can't get just from, say, adding more data to an existing model. I mean, that can help, and it can certainly help if your training data is shifting. But often what you want to do is you want to increase the number of parameters you have to fully capture that and get the benefits of over-parameterization. And then you're back in the situation where you need to retrain the whole model.
All right. Well, I think that wraps it up for today. It's also, you guys were the last speakers of the semester. So thank you very much, Lindsay and Neil. That was actually, let me, before I let you go, Neil, if people wanted to read more about this, is there a paper, or are these slides accessible? What's the best way?
So the slides are not yet accessible, and I'd ask people not to like take anything outside into the public yet, but we will hopefully be submitting on archive within a couple of weeks. Maybe I can send it to IDE and they can circulate the link so that people can get it done.
Yeah, please. We would love to be able to do that. Thanks very much. And thanks to everyone who participated. We'll keep you posted as the fall seminar gets underway. Be well and stay safe.
Thank you.
Thanks, everyone.
Thanks, everybody.
Thanks, everyone.
Thank you. Bye.
Neil, you have one more question. Can you hear me?
Yep. Go ahead.
There's one question in the Q&A. Do you want to answer, and I can email it to the guest, or do you see it?
The question is
In the Q&A, here.
that's the use of machine learning.
Yeah, here it is. Oh, just kidding.
Yeah, so I think, Raphael, I think I need a little bit more. I mean, I think sort of one, so I think one thing I would say is that, and you feel free to clarify if you want to. I think what this is telling us is that certainly, like, while you can be economically affordable, there's a lot of value in using these really big data, really flexible models. But I think that ultimately what it means is that we need to sort of project forward and say, well, if it looks like these models are pretty quickly going to become unaffordable, we're going to have to move to other techniques. And what we want to say is, like, how much extra efficiency can we get while only sacrificing a little bit of performance, or maybe even no performance, right? Maybe you can learn something from the deep learning models that you did, the flexible models that you did, to actually come up with a simpler model. And so, like, Max Tegmark, for example, did a presentation yesterday in the Computers, Brains, Minds, and Machines seminar, which was a very nice example of trying to take a model that's a bit unscrutable and turn it into one that you can really understand. So I think that would be a potential way forward here.
And then there's one more question from Wing Jean. Are there any implications on the market structure? It seems only larger firms can actually afford it and benefit.
Absolutely. So this is something that I think in the short run is something that's very, very interesting and important, right? So, you know, what we see in computing more generally when we see this computing become incredibly expensive is that the number of people using it and being able to afford it goes way down. So, for example, for weather prediction in the United States, basically everybody relies on the work that is done by by NOAA, the National Oceanic and Atmospheric Administration, and then they process it and they add things or something like that, but they all use that as the baseline because it takes huge supercomputers to calculate it. And I think we're very quickly getting into that mode here as well, where, like, the best image recognition techniques or the best video processing and stuff will all be done only in a couple of places because they're the only ones who are willing to train models that might have cost tens of millions of dollars to train in the first place.